When you turn on your kitchen faucet or you flush a toilet, you don't really think about the pipes.
No, not at all.
You just trust the plumbing. Like the clean water comes in, the dirty water goes out. It's totally out of sight, out of mind.
Right, until it isn't.
Exactly. It is only when a pipe bursts in the walls and completely floods your kitchen that you suddenly care very, very deeply about how the plumbing works.
Yeah, it becomes an all-consuming obsession. You're suddenly staring at blueprints, trying to figure out where the main valve is, and you're wondering how something so hidden could cause so much catastrophic damage to your house.
And today, for this deep dive, we are looking at a stack of notes and research focused on a concept called biogeochemical flows.
Which is quite the mouthful.
It is a massive academic
Yes.
mouthful. But the core idea here is that we are looking at the blueprints of the Earth's plumbing.
Mm-hmm.
Our mission today is to answer one massive overarching question from these sources.
Right.
How much can humans alter the Earth's nitrogen and phosphorus cycles before we fundamentally break that plumbing, and in doing so, undermine ecosystems and human society itself?
Because that is exactly what we're doing. I mean, we are dealing with planetary limits here.
Yeah.
We're pushing the global plumbing system to a pressure point that was just never designed to handle.
Okay, let's unpack this.
Yeah.
Because to understand how we're breaking it, we really need to understand what this plumbing actually is.
Yeah.
And the word itself, biogeochemical, it gives us the map.
It does.
You have the bio, which is all living organisms. You have the geo, which is the earth itself, right? The rocks, the oceans, the soils.
Mm-hmm.
And you have the chemical, the elemental building blocks of life moving between them. It's a constant natural recycling system that they've been running on autopilot for, well, billions of years.
Billions, yeah. And it operated under very strict natural constraints. Like the Earth had a specific rhythm. But the context we really need to grasp today is that modern humanity has essentially taken a wrench to those pipes and completely rewired the flows. And the two most critical elements in this vast rewiring project are nitrogen and phosphorus. We've altered how these two elements move across the planet on a scale that is just entirely unprecedented in geological history.
I mean, calling us a geological force feels like something out of a science fiction movie.
Right.
But when you look at the sheer tonnage of elements we're moving around,
Yeah.
it is completely accurate.
It really is.
But to grasp how we broke this system, we have to look at the incredibly brilliant, almost desperate way we tried to fix a fundamental biological problem.
Getting nitrogen into plants.
Exactly. We had to figure out how to feed the plants.
Because nitrogen is non-negotiable for life.
Right.
Like every single living cell requires it. It is a fundamental building block of amino acids, which, make up proteins. It's in our DNA, our RNA.
Right.
And for plants, it's a core component of chlorophyll, the molecule that allows them to photosynthesize and grow. So without nitrogen, biology simply grinds to a halt.
Which brings us to a staggering irony in all of this.
Yeah.
Our atmosphere is roughly 78% nitrogen gas, or N2. I mean, we are swimming in it.
We are.
Every time you take a breath, you are inhaling mostly nitrogen. It's like dying of thirst while stranded in a lifeboat in the middle of the ocean.
Oh, that's a great way to put it.
The plants are absolutely starving for this nutrient, right? Their growth is entirely bottlenecked by it, but they cannot drink the inert nitrogen gas that is completely surrounding them.
That lifeboat analogy captures the frustration of early agriculture perfectly. And the reason they can't drink it, it just comes down to chemistry.
Okay.
So atmospheric nitrogen, N2, consists of two nitrogen atoms bound together by a triple covalent bond.
A triple bond.
Yes, and that triple bond is one of the strongest chemical bonds in nature. It is incredibly stable. It's basically locked in a vault, completely inert and just unwilling to react with anything else.
So the nitrogen is there, but it's biologically useless in that form.
Exactly. For plants to actually use it, that triple bond has to be smashed apart so the individual nitrogen atoms can bond with hydrogen or oxygen to create biologically available forms.
Like ammonia.
Right, ammonia or nitrates. And this process is called nitrogen fixation. And historically, the only phenomena on Earth powerful enough to break that triple bond were literal lightning strikes.
Wait, really? Lightning?
Yeah, lightning, which obviously carries immense electrical energy. And aside from that, just a few highly specialized microorganisms like the bacteria that live on the root nodules of legumes.
Wow. So for thousands of years of human history, our entire global food supply, like how many people we could feed, how fast our civilizations could grow, All of that was entirely limited by how much nitrogen a thunderstorm or some bacteria in the dirt could pull out of the air
Precisely. We were completely bound by nature's speed limit.
until the early 20th century.
Right. What's fascinating here is how humanity decided we were no longer going to accept that biological bottleneck. Two scientists, Fritz Haber and Carl Bosch, they developed an industrial method to completely circumvent nature.
The Haber-Bosch process.
Yes. They built these massive steel reactors, pumped in atmospheric nitrogen and hydrogen gas, and they subjected them to unimaginable heat and crushing pressure.
Just massive force.
Yes, and they essentially forced that triple bond to break.
So they basically recreated the energy of a lightning strike inside a factory.
They absolutely did. They figured out how to industrially convert atmospheric nitrogen into liquid ammonia for fertilizer. I mean, it was industrial alchemy.
They figured out how to pull bread out of thin air.
Exactly.
It's almost impossible to overstate how revolutionary this was. The global population exploded over the last century, largely because of this single invention.
Yeah, without a doubt.
We finally solved the starvation problem. We could make infinite fertilizer, but in doing so, we flooded the world with enormous, completely unnatural quantities of this newly reactive nitrogen.
Which brings us face to face with a massive sustainability paradox.
Here's where it gets really interesting. We can call this the nitrogen paradox. We desperately need this reactive nitrogen to keep billions of people alive, right?
Right. We can't go back to relying on lightning and legumes.
No, not at all.
Yeah.
But the crops we plant, they don't absorb all the fertilizer we dump on them.
They don't even come close. Nitrogen does not just sit politely in the soil waiting for a corn stalk to drink it up. To really understand the scale of the plumbing leak here, we have to trace the journey of a single nitrogen atom.
Okay, let's trace it.
Imagine it starts in one of those massive Haber-Bosch factories. It gets synthesized into ammonia, bagged up, shipped across the country, and then a farmer sprays it onto a massive field in the Midwest.
Right.
The crop takes up a fraction of it, but a huge portion is left behind in the soil. And then the sky opens up and it rains.
And the atom escapes the farm.
Yes, the water washes it right out of the soil. It leaches into the groundwater, or it runs off the surface into a nearby drainage ditch. From that ditch, it flows into a stream, then into a major river system, say the Mississippi River, and eventually it empties out into a coastal estuary or the ocean.
Wow.
This is a biogeochemical flow in real time. We've moved a chemical from the air to the land to the sea.
Then when all that excess, highly reactive nutrient enters the aquatic ecosystems, it does exactly what it was designed to do on the farm, right? It acts as a fertilizer.
Exactly.
So we are basically accidentally fertilizing the oceans and lakes,
Yes.
which triggers a process called eutrophication. You see photos of this happening in places like Lake Erie, where the water turns into this thick, neon green, toxic-looking soup.
It's a biological explosion. The excess nitrogen causes rapid, unchecked growth of algae. The surface of the water just chokes with it. But algae have very short lifespans.
Yep.
So after they gorge on the nitrogen and they bloom, they die in massive numbers. All that dead organic matter sinks to the bottom of the lake or the ocean floor. And that is when the real disaster happens.
Because something has to clean up all that dead algae.
Right. Bacteria begin to break down and decompose that massive blanket of dead algae. But those bacteria require oxygen to survive.
Oh.
So as they feast on the decomposing matter, they consume almost all the dissolved oxygen in the surrounding water.
So we are essentially suffocating the water.
Yeah.
Like the oxygen levels plummet, and any fish or crabs or aquatic life trapped in that area, they either flee or they just straight up suffocate.
It creates what we call hypoxic zones, more commonly known as dead zones.
Dead zones.
Yeah. There is a dead zone in the Gulf of Mexico, fueled by fertilizer runoff from the Mississippi River, that can actually grow to be the size of New Jersey.
The size of New Jersey. That is wild.
So if you trace that back, that single nitrogen atom traveled from an industrial factory to a farm field in Iowa just to suffocate a coastal ecosystem hundreds of miles away.
That is horrifying. But at least the damage is contained to water, right?
Yeah.
The runoff is a liquid problem.
I really wish I could say it was contained to the water, but that nitrogen atom doesn't just flow downward, it also goes up. Yeah, reactive nitrogen is incredibly volatile. So a significant portion of the fertilizer applied to fields volatilizes, meaning it turns into a gas and enters the atmosphere as ammonia.
Which causes severe air quality issues.
Right. It combines with other emissions in the air to create dangerous particulate matter, and that causes severe respiratory problems in communities miles and miles away from the farms.
Wow.
But it gets worse. Biological processes in the soil, performed by other microbes, can transform that excess nitrogen fertilizer into nitrous oxide, or N2O.
Nitrous oxide. Wait, that's a greenhouse gas.
It is an incredibly potent greenhouse gas. It traps roughly 300 times more heat in the atmosphere than carbon dioxide over a 100-year period.
300 times.
Yes, and it also depletes the ozone layer. If we connect this to the bigger picture, it shows us exactly why a planetary boundary is never just a single, isolated issue.
Yeah.
Nitrogen connects agriculture directly to freshwater health, to ocean suffocation, to toxic air quality, and to global climate change. One human intervention cascades across space and time. It's a sequential chain of environmental destruction known as the nitrogen cascade.
It's like pulling the plunger on a pinball machine and just launching a wildly chaotic metal ball that keeps hitting bumpers. It scores negative points for the environment. Everywhere it bounces, water, air, climate, and you can't get the ball back.
Yeah, it's a pinball machine where the ball multiplies every time you hit the flippers.
Okay, so hearing about this cascade, my brain immediately jumps to what seems like the most obvious pragmatic solution here. Precision.
Okay.
If the runoff and the escape of the atom is the problem, why don't we just engineer better farming practices? Like, if a farmer can use GPS and soil sensors to improve their nitrogen use efficiency, say making sure the plant absorbs 60% of the fertilizer instead of just 40%, doesn't that fix the issue? Like, we just use less, but use it smarter. We don't release the pinball.
It sounds perfectly logical. We assume efficiency equals sustainability.
Doesn't it?
No, this is a classic trap in environmental systems management. It is the illusion of efficiency versus sufficiency. Let's look at the underlying math of how this actually plays out in the real world.
Okay, lay the math on me.
Suppose a farmer is managing a field and applies 100 kilograms of nitrogen fertilizer.
Okay, 100 kilograms.
Under standard conditions, the crop absorbs 40 kilograms. That's a 40% efficiency rate.
Right.
That leaves 60 kilograms of nitrogen left behind to leach into the water or escape into the air.
Got it. 60 kilograms of pollution.
Now let's introduce your solution. Through incredible new technology and precision farming, the farmer improves their efficiency to 50%.
Nice.
The plants are much better at taking up the nutrients, but because global demand for food is skyrocketing and the fertilizer is highly effective, the farmer decides to intensify production.
Oh, cool.
So they double their total fertilizer use to 200 kilograms.
Which makes sense for the farmer. I mean, they want to maximize their yield to feed more people and, make a living.
Exactly. So at 50% efficiency, the crop successfully absorbs 100 kilograms of nitrogen. That is a massive win for food production. But what happens to the rest?
Well, 50% of 200 is 100. Wait.
Yes, 100 kilograms of nitrogen lost to the environment.
Oh, wow.
The farmer's efficiency went up significantly, but the total environmental pollution still climbed from 60 kilograms to 100 kilograms.
That is just wild.
Improving efficiency per plant or per acre does not automatically reduce the total environmental pressure if the absolute scale of the agricultural system keeps expanding.
Right.
It's known as Jevons paradox. As we get more efficient at using a resource, we often end up using more of it in total, not less.
Because we have an infinite supply of nitrogen from the Haber-Bosch process, efficiency just encourages us to grow the system faster, which is a perfect, albeit depressing, transition to the other half of this planetary boundary. Because if efficiency can't save us with nitrogen because we can essentially conjure unlimited amounts of it from the thin air, what happens when we build our entire global food supply on a nutrient that we cannot manufacture?
Right.
Because that is the terrifying reality with phosphorus, isn't it?
It is entirely different stakes here.
Yeah.
The distinction between nitrogen and phosphorus is one of the most critical concepts in understanding global agriculture.
Okay.
As we establish, nitrogen has a massive atmospheric reservoir. We can pull it from the sky forever as long as we have the energy to break that triple bond.
Right. Lightning in a bottle.
But phosphorus has no atmospheric component. There is no phosphorus gas in the air for us to harvest.
So where does it come from?
It is strictly bound to geology. It is locked in rocks, ancient soils, and deep marine sediments.
Wait, marine sediments.
Yeah. Millions of years ago, the oceans were teeming with life that absorbed phosphorus. When those organisms died, they sank, they accumulated on the seafloor, and over geological timeframes, tectonic pressure turned them into phosphate rock.
Meaning we have to mine it. We are literally digging up millions of years of ancient geological history just to sprinkle it on next season's corn crop.
Exactly. We mine it out of the ground using massive open pit operations in places like Morocco, China, and the United States. We crush the rock, treat it with acids, and refine it into soluble fertilizer.
So if nitrogen is like pulling endless amounts of a chemical out of thin air until we literally choke on the excess, phosphorus is like draining a limited, non-renewable family bank account to buy things that eventually end up crashing our own house.
That is a very grim but incredibly accurate summary.
Yeah.
And this creates a dual crisis, often referred to as the phosphorus paradox. On one hand, you have the exact same pollution dynamic as nitrogen. The excess phosphorus that washes off the fields is a potent trigger for the severe eutrophication and those dead zones we talked about in freshwater lakes.
Right, the algae blooms.
It is a massive pollutant, but on the other hand, phosphorus is a strictly finite mineral resource.
We can't just invent a Haber-Bosch machine for rocks.
No, we cannot. There's only a certain amount of high-quality, economically viable phosphate rock in the Earth's crust, and modern agriculture is completely 100% addicted to it.
Wow.
Without mined phosphorus, crop yields would crash globally.
So we are rapidly running out of the exact same chemical that is actively polluting our lakes and rivers when we use it. We are throwing our limited bank account down the drain.
We are hurtling toward a horizon where, when the accessible phosphate rock runs out, our ability to feed billions of people goes right with it.
So let's look at the physical map of this. We are pulling millions of tons of nitrogen from the sky. We're dynamiting millions of tons of phosphorus out of the Earth's crust. We aren't just farming. We are a geological force, moving mountains of elements. But it's not just spreading out evenly across the globe, right? Like, where's all this stuff actually going?
That is the core of the plumbing issue. The flows are highly concentrated. Our modern food systems are designed to funnel massive amounts of these elements into very specific, geographically dense locations. Think about industrial livestock operations.
Like massive cattle feedlots.
Right. We grow nutrient-dense crops like soy and corn across millions of acres, and then we ship all that harvest to feedlots where thousands of animals consume it.
Right.
But animals aren't perfectly efficient either. A massive proportion of the nitrogen and phosphorus they eat passes right through them and is excreted as manure.
So you have millions of acres of harvested nutrients suddenly concentrated into just a few square miles of cow manure.
Exactly. And the local soil around that feedlot simply cannot absorb that staggering volume of nutrients. The plumbing backs up.
Yeah, that makes sense.
It oversaturates the ground, it leaches deep into the groundwater aquifers, or it runs directly into local river systems during a rainstorm. And human cities do the exact same thing, just with different infrastructure.
So cities are just massive feedlots for humans.
From a biogeochemical perspective, yes.
Wow.
A megacity is a massive nutrient processing funnel. Food flows into the city via trucks and trains from agricultural regions all over the world.
Yeah.
Millions of people consume those nutrients daily, and then they excrete them directly into the municipal sewage system.
Right into the pipes.
If that urban wastewater isn't treated with rigorous nutrient recovery technology, a city is essentially a fire hose pumping thousands of tons of reactive nitrogen and mined phosphorus directly into rivers and coastal waters.
We aren't a cycle at all. We are just a massive linear conveyor belt for the Earth's geology.
And that conveyor belt often creates heartbreaking trade-offs. The history of the Green Revolution in India is a perfect, complex setting to understand this.
Ooh, let's dig into that. Because the Green Revolution is usually heralded as one of the greatest triumphs of the 20th century.
And it was. By introducing high-yielding crop varieties, expansive irrigation, and heavily subsidized synthetic fertilizers, India completely transformed its agricultural productivity.
Right.
It was a massive, undeniable victory for human survival. It pulled millions of people back from the brink of absolute starvation and secured their food supply.
But the plumbing couldn't handle the pressure.
The environmental hangover was severe. The nitrogen cascade occurred in full force. Massive runoff led to degraded water systems. Groundwater became contaminated with nitrates, which is a severe health hazard for drinking water.
Oh, yeah.
And the natural fertility of the soil was heavily compromised by over-application.
So we traded a starvation crisis for a biogeochemical crisis.
If we connect this to the bigger picture, the lesson from India is not a simplistic, fertilizer is evil narrative.
Yeah, because it saved lives.
Exactly. Fertilizer saved lives. The lesson is that when a powerful technology is deployed to solve a dire, immediate societal problem, It can easily create entirely new environmental catastrophes if it is pushed far beyond the wider ecosystem's capacity to absorb it.
Wow.
Systems have limits. That is what planetary boundaries force us to confront. Where does the nutrient go after it does its job, and can the Earth survive it?
Okay, so if the whole system is this deeply interconnected, like if we can't solve it just by making plants a little more efficient, and we obviously cannot just ban synthetic fertilizer tomorrow without starving half the planet, how do we actually fix the plumbing?
This raises an important question, and it is fundamentally a question of justice.
Justice.
Yes, planetary boundaries are not just cold ecological math, they are about human equity. We have to look at who is benefiting from this broken plumbing and who is drowning in the leaks.
Right. The agricultural corporation gets the higher yield, the global consumer gets cheaper bread, but the local fishing community downstream in the Gulf of Mexico gets a toxic dead zone. They lose their entire livelihood so someone else can have cheap corn.
Exactly. The costs and benefits are entirely divorced from one another. And on a global geographic scale, this creates a bizarre imbalance.
How so?
Imagine two regions of the world. In Region A, say parts of Western Europe or the American Midwest, you have decades of historical, incredibly intensive fertilizer application. The soils are practically saturated, the groundwater is polluted, and the core problem is too much nutrient.
Right. They are drowning in excess.
But in Region B, like many parts of sub-Saharan Africa, the soils are naturally weathered and nutrient poor. The farmers there struggle daily to maintain basic food production, and they simply do not have the economic access to synthetic fertilizers.
Oh, I see.
Their core problem is too little nutrient.
So establishing a safe and just planetary boundary doesn't mean capping everyone globally at the exact same arbitrary limit?
Correct. It means redistributing the flow. It means finding a global balance where regions that are starving for nutrients have enough to meet their fundamental human needs, while forcing the regions that are grossly overpolluting to radically scale back so that the global ecological systems are not overwhelmed.
So what does this all mean for you listening right now? How do we shift our perspective from seeing this as just a niche issue of farm pollution to recognizing it as a fundamental design flaw in how humanity operates?
We have to redesign the conveyor belt I mentioned earlier.
The straight line.
Right. Right now, our path is a wasteful straight line. We mine the rock in Morocco or fix the nitrogen from the air in a massive factory. We turn it into fertilizer. We put it on a farm. We transport the crop to a city. A human eats it. A human excretes it. And the sewage system flushes it straight into the ocean. Extraction to pollution.
A straight line to a dead zone.
The only viable solution for the future of humanity is to transition to a circular nutrient economy.
What's circular?
We have to physically bend that straight line into a closed loop. Farm to food to city to waste, and then the critical missing step, nutrient recovery.
Wait, meaning we pull the nitrogen and phosphorus out of the sewage?
Yes. We have the technology to extract those exact elements from urban wastewater and agricultural runoff, treat them safely, and package them as high-quality fertilizer to be returned directly to the farm.
That is amazing.
We must stop treating sewage and runoff as a hazardous waste problem and start treating it as the most valuable raw material for the next crop.
That is mind-bending. It's honestly incredible to marvel at the journey of a single chemical atom, from an industrial Haber-Bosch reactor, raining down on a stalk of wheat, getting baked into a loaf of bread, eaten by a person, flushed through a dark city sewer pipe, and flowing out into the vast ocean.
It really is incredible.
We literally cannot exist without these elements. Our bones, our blood, our cells are built from them. But we have to manage the planetary plumbing so much better than we are now. We can't just leave the faucet running on maximum volume and pretend we don't notice the basement flooding.
No, we can't. We have to evolve from being mere consumers of these flows to becoming active stewards of the cycles. If we keep the resources in productive use, rather than constantly extracting and discarding, we can step back from the edge of the planetary boundary.
Which leaves us with a final thought to mull over. If humanity continues to aggressively pull nitrogen from the atmosphere, and if we continue to mine finite dwindling reserves of phosphorus from the earth, only to flush all of it straight into our massive urban centers, could the city wastewater treatment plants of the future become the most valuable mines on Earth? Imagine a future where we don't blow up mountains for fertilizer or burn massive amounts of fossil fuels to force it from the sky, but literally harvest it directly back from the depths of our own cities. The ultimate closed loop.